Hello, problem solvers. Let's talk about Chapter 9, Solve an Easier Related Problem is the name of the strategy. Let's take a look at an example. In your reading notes, you wrote down there like kind of the professor broke down like 6 different kind of categories of or ways that solving an easier related problem could look like. And this is one of those ways. So let's take a look at this. The clerk of Simpletown has the job of getting materials ready for the next municipal election. There are 29 issues and candidates. In the last election, there were 28,311 registered voters representing 18,954 households, and they voted at 14 polling places. The clerk figures she needs a proportionate amount of materials for this election. This time, though, there are 34,892 people registered to vote. So how many polling places will be needed? So the first thing we need to do is identify the fact that some of this information is information we don't need to answer this question. So we need to kind of pay attention to the fact that to figure out the polling places, it's kind of just based on the people, doesn't matter how many issues there are. It also is based on the number of registered voters, doesn't matter how many households, and I don't even know how many households there are now. So the numbers that I'm going to need are in the last election, there were this many registered voters and they used this many stations. So there are now this many registered voters and I want to figure out the number of polling places. So those are the numbers I'm going to use. But I'm going to make this problem much easier. And one of the methods to do that is to just use easier numbers. Not necessarily numbers that are smaller, but numbers that are rounded. So what I'm going to do is I'm going to instead say that this number is about, and I'm going to round a lot, I'm going to say that that is about 30,000 people. And then I'm going to say this is about 35,000 people. And then this number, like 14 doesn't go into that nicely, but you know what does? 15 does. So I'm going to just say, okay, let's call that 15. And let's see where we are. And now the nice thing about using these numbers is this math you can do in your head. So for example, last time there were about 30,000 voters and they needed 15 polling places. And then 30 divided by 15 is 2. So that's 2,000 voters for every polling place. So now it's pretty simple then, because now we have about this many registered voters, 35,000. So all I do is divide that 35,000 by 2,000, which, again, you can do that in your head because that's the same as 35 divided by 2. And 35 divided by 2 is 17 and a half. So that tells me a rough estimate of around 17 and a half polling places. Now, because I rounded, I know that the number I want will probably be somewhere between 17 and 18. And then based on the situation, I'll have to decide, whether I want to go down to 17 or up to 18. And you can see if you end up doing the same problem with the actual numbers that you started with, like you could set up and solve a proportion, and when you actually don't round, you get 17.25. So you can see we were pretty close there using nice rounded numbers. So that's one way to make a problem easier, is to round the numbers. And that was one of those 6 ways you identified in your reading notes. Next, let's take a look at another problem here. And this is one of my favorites. How many squares are there on a checkerboard? That's it. That's the question. Here's a checkerboard. Okay. It is 8 by 8. And I will give you a hint. There are not 64 squares. There are actually way more than that. Now, if you're not sure what I mean by that, because if you count these squares, there are 64 maybe, you think. But here's what I'll say to that. Take a look at this square right there. There's a square on this checkerboard. It happens to be bigger than these 1 by 1 squares. This is a 3 by 3 square right there. That's another square on this checkerboard. And hey, look, there's another 3 by 3 square right there. And another one right there. And another one right there. And actually another one right there. And another one right there. So you can see they're actually overlapping, but they're different squares. Now, we could do that same thing for all sorts of sizes of squares. So when you think about that, how would you count how many squares there are on a checkerboard? I'd like you to give that a try on your own here. So go ahead and press pause and then press play when you're ready to check what you did. All right, let's take a look. First, I'm going to show you how you might approach this problem using subproblems, which this is not the strategy from this chapter. But here's what subproblems might look like. You might say, okay, how many 1 by 1 squares are there? So you count up all these little squares and there are 64. And then you say, okay, how many 2 by 2 squares are there? So you count how many 2 by 2 squares there are. So those would be squares like that size. So there's 1 and 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7 more, and 7 more, and all the way down. So every row basically has 7 more, but there's 1, 2, 3, 4, 5, 6, 7. So really it's 7 by 7. So there's 49 of those. And then how many 3 by 3 squares? Well, you can do the same thing with the 3 by 3 square. And you can say, okay, there's 1, 2, 3, 4, 5, 6, and so on, 6 more and 6 more, all the way down to your 6th row of 3 by 3 squares there. And then you can keep doing that all the way up to 8 by 8 squares. And then you can see you add up the numbers 64, 49, 36, and so on. Those are all perfect squares to get a total of 204. So that would be the strategy subproblems. What I'd like to do, though, is focus on how you might solve this problem using this new strategy, solving an easier related problem. So instead of asking these subproblems, I'm going to reword it. I'm going to make the problem easier by just pretending the checkerboard is way smaller. So how many squares would there be on a 1 by 1 board is the question I'm going to try to answer instead. Notice if it's just 1 by 1, well, then there's just 1 square and that's it. And turns out answering this easier related problem didn't really help me at all. And that might happen. So what I'm going to do is I'm going to say, okay, let's make the board a little bigger. This is still going to be a much easier related problem, but let's go on to, okay, what if I had a 2 by 2 board? So how many squares are there on this? Well, there are 4 little squares and then 1 big square for a total of 5 squares. And I might not still know how to approach that original problem because this board's so much bigger, so I'm going to do another easier related problem and say, okay, let's answer this now for a 3 by 3 board. So how many squares are there on this board? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 little squares. Okay. And then how many 2 by 2 squares? Well, 1, 2, 3, and 4. There are 4 2 by 2 squares. And there's 1 3 by 3 square for a total of 14. At this point, you might notice a pattern here. And to check that pattern, so here it is arranged a little bit different way, maybe a little more organized, a little more clear. To check that pattern, I'm going to do the same thing with a 4 by 4 checkerboard. So there's 16 little squares. There's 9, I'll call them medium squares, 2 by 2 squares. You can count up. There's 9 of them. There are 4 3 by 3 squares, so those maybe are large squares, 3 by 3 squares. There are 4 of them. And then there's 1 big square, 1 big 4 by 4 square. And you might at this point notice that all these numbers are perfect squares. So this is 4 squared, this is 3 squared, this is 2 squared, this is 1 squared. And this first number is 4 squared, which 4 was the dimensions of the board. So if I use that same pattern, I've now recognized a way to answer a question like this for any size board. So if I use that same pattern for this board, I can just say, well, I know because it's 8 by 8, I'm going to start with 8 squared and add up all the numbers all the way down to 1 squared. So I just write out all those, I add them all up, and I get a total of 204. Now for this strategy, I want to stress that you also need to write an explanation. So here's what that explanation would look like. And this is a lot of stuff I just said out loud. So you can see I wrote out my process. I started by answering the easier related question, how many squares are on a 1 by 1 board? I found that there was just 1. This didn't help me find a process to answer the original question, so I then answered the same question for a 2 by 2 and a 3 by 3 board. For the 2 by 2, I found there were 4 small and 1 big square, and for the 3 by 3, I found there were 9 small, 4 medium, and 1 big square. At this point, I noticed a pattern, which I checked by answering the same question for a 4 by 4 board, which had 16 small, plus 9 medium, plus 4 large, plus 1 big square, I noticed that the numbers I added up were perfect squares, starting with the dimension of the board and going down to 1 squared. So for an 8x8 board, I added up 8 squared plus 7 squared plus 6 squared plus 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared equals 204. So some of the key things here for this strategy: make sure you organize your information, simplify your numbers, we saw that in the first example, and also ignore irrelevant information. For your homework, I want to stress, please make sure you actually are trying to use this new strategy. Even if you think there's another strategy you would like to use, try this new strategy, because we're trying to learn this new strategy, and I'd like you to practice it. And for this strategy, remember, you must include an explanation for your solution. So that's it. Thanks, and please let me know if you have any questions.